Okay, so now we are going to see a very beautiful application of all that we have learnt so far, integration and convergence and so on and so forth, and prove a very classical theorem from analysis which we have already seen surely in a course on real analysis. So we will prove the Weierstrass's theorem. So the Weierstrass's theorem or Weierstrass approximation theorem tells you that any continuous function on a bounded interval can be uniformly approximated by a sequence of polynomials. So this is the Weierstrass approximation theorem, and so let us try to prove this in a completely different way using the notions of integration which we have been seeing. So we work with the interval x equals 0, 1. And if x naught belongs to x, we denote by delta x naught equals the Dirac measure concentrated at x naught. So recall, so this means delta x naught of E equals 1 if x naught belongs to E, and 0 x naught is not in E. So this is the Dirac measure, and of course sigma algebra is the entire power set, every subset is measurable. Okay, so now we take t to be in 0, 1 and n natural number which is fixed, and then we define mu and t. X of course is still 0, 1 and S is the power set of x. Okay, so now we are going to define a measure. It has two indices, one is n, the natural number, and t which is fixed in 0, 1. So m and t is, mu and t is defined as sigma k equals 0 to n nck t power k 1 minus into 1 minus t power n minus k delta at k by n. Okay, so we have delta, this maybe need not put these brackets here unnecessarily, delta of k by n. So we have a linear combination of n Dirac measures, so that's again a new measure. So when you multiply a measure by a constant, it's a measure, then you add two measures, you can obviously define another measure, and therefore this is a linear combination of several measures, and you have this measure. So what is nck? This is the usual binomial coefficient. This is n factorial by k factorial into n minus k factorial. Okay, so let us, so we have fi of x, we define as x power I, 0 less I equals 0, 1 and 2. So f naught is identically 1, f1 of t is t, and f2 of t of x, sorry. And f2 of x equals x square. So we will now compute all these integrals of these functions with respect to this measure. So it's a good exercise in computing these things. So what is mu and t of x? So mu and t of x is nothing but integral f naught d mu and t over x, and so you have to just evaluate. Integral with respect to Dirac measure is just evaluation, so evaluation at the point k by n, and that's always equal to 1 because f naught is identically equal to 1. So this is equal to k equals 0 to n of nck t power k 1 minus t power n minus k and into 1, and this you know is nothing but 1 plus t plus 1 minus t whole power n, and that's equal to 1. Now let's compute the integral f1 d mu n t. So this is equal to sigma k equals 0 to n nck t power k 1 minus t power n minus k into delta k by n. I have to integrate f1 against that measure, and that is nothing but evaluation of the function f1 at the point k by n. f1 is just the point x, so I just get k by n. So integral f1 delta k d delta k by n over x is nothing but f1 evaluated at k by n, and that's equal to k by n. Okay, so that's what we have. So now let me pull out the t, that is sigma. K equal to 0 will cease to exist because the k equals 0 is here, so that it will give you 0. So I just write from k equals 1 to n nck t power k minus 1 1 minus t power n minus k into k by n. Okay, so now we do some jugglery with this. This is equal to t times sigma k equals 1 to n nck t power k minus 1 1 minus t to the n minus k I write as n minus 1 minus k minus 1 because I want the same exponent in both these things here, and k by n. Now nck into k by n, this is equal to n minus 1 factorial by k minus 1 factorial into n minus k factorial. Again I can write this as n minus 1 factorial by k minus 1 factorial into n minus 1 minus k minus 1 factorial, which is equal to n minus 1 ck minus 1. So this is equal to t times sigma k equals 1 to n minus 1 ck minus 1 t power k minus 1 1 minus t to the n minus 1 minus k minus 1. Okay, and this is equal to t times sigma k equal to 0 to n minus 1 nck t power k 1 minus t power n minus k, because I have just n minus 1 ck n minus 1 minus k. I just replace k minus 1 by k and change the range of the k. Okay, so that is t times, now again this is t plus 1 minus t power n minus 1, and that's equal to t. So we get integral f1 d mu n t over x is just t. So similarly you can make the calculation. So I will allow you to check this, just playing around with the binomial coefficients. So this is equal to integral x f2 d mu n t. So this, let me just write down k equals 0 to n nck t power k into 1 minus t power n minus k, and then integral f2 d delta k by n over x, and that is k by n whole square. Okay, so then that is equal to 1 by n into n minus 1 t square plus t. So yeah, just check it, it's just again algebra. So now if you write fx equals x minus t the whole square, that's equal to x square, which is f2 of x, minus 2t times x, which is f1 of x, plus t square f0 of x. And therefore, integral f d mu nt over x is equal to, if you then substitute, we have all calculated all these three things, you will simply get t minus t square by n. Now, maximum value of t minus t square by n on 0, 1, you can check it by you classical maxima minima will occur at t equals half, so this will be equal to 1 by 4n. So lemma, let t belong to 0, 1 and n in n fixed. Let epsilon be greater than 0. A epsilon equal to set of all x in x such that mod x minus t is greater or equal to epsilon. Then mu of a n t of a epsilon converges to 0 as n tends to infinity uniformly with respect to t. Okay, so proof. So we are going to take integral x minus t whole square d mu nt over x. So that is greater or equal to integral over a epsilon x minus t whole square d mu nt. But on a epsilon, this is bigger than or equal to epsilon, so this implies that epsilon square mu nt of a epsilon is less than or equal to integral over x minus t whole square d mu nt, and that we have already calculated, that's equal to t minus t square by n, and that's less than or equal to 1 over 4n as we already saw. So this implies that mu nt a epsilon is less than or equal to 1 by 4 epsilon square into 1 by n, and that goes to 0 as n tends to infinity, and it's independent, the rate at which it goes to 0 is independent of t, so uniformly with respect to t. Because this right hand side is independent of t, and therefore that convergence is uniform with respect to t. So then lemma again. Let f belong to C01. T in 01 fixed. Then limit n tending to infinity integral f d mu nt over x equals f of t, and convergence is uniform with respect to t. Proof. So f continuous on 0, 1 compact interval, so f is uniformly continuous. So given epsilon positive, there exists delta positive such that mod x minus y less than delta implies mod fx minus fy less than epsilon. So you take a delta to be the sort of all x in x such that mod x minus t is greater or equal to delta. T is fixed, you remember, so we have let t. Okay. Now f of t is a constant, so this is equal to integral of f of t into d mu n t. F of t is just a number, and this is with respect to, so this is a constant, okay, constant. Okay, so now we are going to take modulus of integral over x f d mu n t minus ft. That's equal to modulus integral over x f minus f of t let me write f of x minus f of t d mu n t. I'll write the variable x here because now we are integrating with respect to the variable x. Okay, and that is less than or equal to integral over x mod fx minus ft d mu n t x, and I am going to write this as sum of two integrals I1 plus I2. So I1 is equal to integral over a delta mod fx minus ft d mu n t x, and I2 equals integral over a delta complement of mod fx minus ft d mu n t. Again, the integration is with respect to x. Now I1, so let us assume that mod fx is less than or equal to m for all x in 0 1, because it is a continuous function and therefore it is bounded. Okay, so this is less than or equal to, so here fx minus ft is less than or equal to 2m times integral a delta of d mu n t, which is just mu n t of a delta, which is less than or equal to, we have already computed this, so this is less than or equal to 2m by 4n, yeah, it's a into delta square. Okay, this is what we have. Now I2 is what? Now I2 is, on I2 we have mod x minus t is less than delta, so that means mod fx minus ft is less than epsilon. So this is less than or equal to epsilon times mu n t of a delta complement. We know nothing about that, but that is less than or equal to epsilon times mu n t of x, which is equal to epsilon, because mu n t of x is equal to 1. So now, given eta positive, choose epsilon less than eta by 2. This fixes delta. Then choose capital N such that for all n greater or equal to capital N, we have 4m by 2m by 4n delta square is less than eta by 2. Then for all n greater or equal to n, you have I1 plus I2 is less than eta, that is integral mod f d mu n t minus ft is less than or equal to less than eta for all n greater equal to capital N. And capital N depended on what? Depended, first of all, it depended, given epsilon, you choose eta such that it's less than eta by 2, and then having chosen epsilon, delta is automatically fixed, and therefore this again depends only on epsilon. So this N depends only on epsilon and does not depend on t, and therefore this convergence is uniform with respect to t. So that proves the lemma. Okay. So remark, in this proof what did we do? So we split the, so remark, to estimate the integral, we split it into integrals into I1 and I2. I1 was on A delta. We know very little about the integrand, but measure of A delta is small. I2 integrand is small. And measure of A delta complement is less than or equal to 1. Okay. So we split the integral. On one we have information on the measure of the set, on the other we have information on the integral. So using these two complementary informations, we are able to estimate the integral. This kind of divide and rule policy is very helpful. This is a very useful technique to know. Okay, so this is a technique which can come in useful whenever you want to estimate some integrals. Okay, so now let us integral f d mu n t. What is this? Over x. This is equal to sigma k equals 0 to n nck t power k 1 minus t power n minus k and to f k by n. Okay, this is the thing. Now this is a polynomial in T, and therefore we have proved the Weierstrass theorem. So therefore we have proved the following, namely theorem. This is called the Weierstrass approximation theorem. Every continuous function on a compact interval can be uniformly approximated by a sequence of polynomials. We have done it on 0, 1, but you could have done it in any other interval accordingly, or you prove it for 0, 1 and then simply by mapping 0, 1 to any finite interval a, b, you can prove it. Those are just jugglery and you don't have to do anything. And this polynomial converges uniformly to f of t uniformly as n tends to infinity. Now this polynomial Bn of t, which is sigma k equals 0 to n nck t power k 1 minus t power n minus k f of k by n, these are called the Bernstein polynomials. Okay, so for each n you have a polynomial, so these are called the Bernstein polynomial. So we have proved simultaneously two things. One is that you can approximate continuous function uniformly by a sequence of polynomials, and we have also identified what those polynomials are, and so all this has come simply by discussing integration with respect to the Dirac measure suitably. Okay, so this is a nice application. So now finally I want to talk a little about probability theory. So we will try to give a dictionary between measure theory and the theory of probability. So what is so a probability space is a measure space. Omega, B and P, where P of omega is 1. Okay, and omega, this is called the sample space. B, the sigma algebra, equals collection of events. So if A belongs to B, then P of A equals the probability of the event A. Event A happening. Okay, so now if B is an event, then you define a sigma algebra BB on subsets of B. We have already done this when defining the integral over subset. So BB is nothing but in set of all intersection A intersection B, A is an event. Okay, and you define a probability on B intersection A intersection B. So PB of A intersection B. Already we've done this before. So this is nothing but the usual probability of A intersection B itself. Okay, but we want to have this as a probability measure, so we divide it by PB of B. P of B, sorry. So that PB of B itself will be 1. So PB of B will be equal to 1. So this is called the conditional probability. So probability of A occurring given B. Given that B is happening, what is the probability of A also happening? And that's precisely the probability measure or probability of A intersection B, and then divided by the probability of B, and you have this. So you have P intersection of P of A intersection B is PA. This is also written as conditional probability of A given B. Okay. Now, two events A and B are independent if P of A intersection B is the same as P of A. So it doesn't matter whether B happens or B does not happen, it does not affect the occurrence of A, and therefore this means that P of A intersection B equals PA into PB. Okay, this is the notion of independence. Now, random variable is nothing but a measurable function. Only in probability theory we use the notation F here, so instead we use value X. So X is a random variable, so we use the symbol X for the set, Now the set is omega, that is a sample space, and therefore random variables are defined by this. So expected value or mean of x is E of x equal to integral x dp. Pointwise convergence almost everywhere of a sequence of random variables xn to x. Okay, then we say xn converges to x almost surely. So if xn converges to x in measure, then we say xn converges to x in probability. So is probability really just measure theory? No, because there is something which is in probability which does not come in study in measure theory. Okay, so namely, so distinguishing feature of probability, namely independence of random variables. So x, y random variables independent if for every pair of Borel sets A and B. So we are talking of real value. So every pair of Borel sets A and B, we have P of x inverse A intersection y inverse B equals P of x inverse A, P of y inverse B. That means given any x inverse A and y inverse B, their sets are independent. Okay, so this is the thing that is whether the random variable x takes value in A is independent of the fact that random variable of y takes the value in B. That's all. So this is what we call independence of random variables. Similarly, distribution function of a random variable x. So this is equal to probability. So f of t equals probability x is less than or equal to t. That is p of x inverse of minus infinity t. Okay. Okay. So x and y are identically distributed if they have the same distribution function. So sequences of independent identically distributed random variables is a very important study in stochastic process. Okay, a stochastic process is nothing but a family of random variables. So it's a family, so you study a family of measurable functions at the same time. So there's a second index which will come in, and therefore you have. So this is some kind of brief dictionary which tells you how to understand the probabilistic language in terms of measure theoretic language. Okay, so now with this I will conclude this chapter on integration, and we will do some exercises before we leave it all together.